Welcome! In this video I'll show you how to solve problem 2.1 as it appears in the third edition of Griffiths' Introduction to Quantum Mechanics. Now this problem asks us to do the following. It says prove the following theorems, and we have part A, B, C. We will of course begin with part A. It says for normalizable solutions, the separation constant E must be real. And then they give us a hint that we should rewrite the energy as E0 plus I gamma, with E0 and gamma real. So basically, we have to allow for the possibility of the energy being complex and then just see what happens, right? What would that imply? Okay, so if we want our solution to be normalizable, that means that, of course, if we integrate over the probability density, right, what this basically means the probability that at a certain time our particle be in a given place, and we add over that over the entirety of space, we have to get 1. And that of course makes sense because the particle has to be somewhere. So if we add the probability of the particle being here, the particle being here, 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 and we go through the entirety of space, we have to get 1 because it has to be somewhere. Okay, so that is the normalization condition. Very important, you have to know and understand this, because you will use this throughout literally like everything that is quantum, quantum mechanics, and everything that goes after that, you will be using this. So you have to learn it. Okay, now let's write this explicitly. So let's separate the x and time solutions as we have done in the lectures. So we have that psi of x times e to the minus I e t over h bar and the modulus squared. We haven't yet used this condition that the energy may be complex. Let's do it now. So let's now rewrite this as the integral of course will not change. And now we write this as minus I, and then we have E0 plus I gamma divided by h bar and times t, and the modulus of all of that squared. Now, how do we calculate the modulus? This is also very important that you understand. So the modulus we calculate, so if we have the modulus of something, which we call just A, right, the modulus squared, this is simply A conjugate A. Okay, so we simply take the conjugate of what we have inside and we multiply through. So this is 1 equal to integral from minus infinity to infinity of, and now we have, instead of the modulus, we will have psi conjugate of x times e to the plus I E0 minus I gamma t divided by h bar. And now we multiply by just regular a, which in this case is psi of x, e to the minus I E0 plus I gamma divided by h bar. And we integrate over all of space. Now notice that the exponents do not depend on space, so we can take them out of the integral. So we'll have an exponent that it will have I t h bar. I will just factor it out in front this time. And then we have E0 minus E0. And then we have this minus there. So we have minus I gamma minus I gamma. And then we have the integral, so we integrate from minus infinity to infinity. And here we have psi conjugate psi, which is simply the modulus of psi of x squared. Okay, so now clearly the E0s cancel out, and we have that 1 is going to be equal to e to the, now we have I squared, right? 1 is going to be here, 1 is going to be there. I will show you explicitly. So we get minus 2I squared t gamma over h bar. However, we have, I squared, which is minus 1. So we can just rewrite this with a plus sign there. So let me just put it all together. So it is 2t and then gamma over h bar. And then we have the integral. And squared dx. Okay, so in order for our solutions to be normalizable, we want that for every single possible time, we want that this expression has to be 1. So it doesn't matter what the value of t is, we want that this is 1, right? So at t equals 0, this has to be 1, right? So because at t equals 0, we have that 1 is equal to the integral of minus infinity to infinity of, what we are used to, right? So, but this time doesn't, the right-hand side here doesn't depend on time. So as time goes on, this integral is 1. So the only possibility is that for every single possible time, this entire exponent, this entire e, has to be 1 as well. So we need that e, actually let me maybe move down so that it's not as chaotic. So we need that e to the 2t gamma over h bar has to be equal to 1. And for that, we need that 2t gamma over h bar is equal to 0. But of course, since time changes, right, we need gamma to be 0. So the only way for this to happen is if gamma is 0, which means since we defined energy to be, some E0 plus I gamma, this means that the energy has to be real. Okay, so there we go. We just proved part A. Now let's go for part B. So for part B, what we need to do is the following. They ask us to show that the wave function here, little psi, which they use to refer to psi of x, can always be taken to be real, unlike big psi, right, which they use to call when it is x comma t, which is necessarily complex, of course, because it has the e to the minus I e t over h bar, like we just saw. Okay, so this doesn't mean that every solution to the time-independent Schrödinger equation is real. What it says is that if you have one that is not, it can always be expressed as a linear combination of solutions with the same energy that are. And this is very important because that means that every single problem, right, that we will encounter will have a real wave function. Even though we may encounter a complex one, we can build a real solution from the complex result that we found. That's what we will prove here. Okay, so how do we do it? Well, we know that, and it's actually one of the hints that they give us here, that we can always build a real solution when we have some. So let's say that psi, right, psi of x is a solution and psi conjugate of x is going to be its complex conjugate. Okay, so if psi of x is a solution and it is complex, then we can find a real solution by doing the following. We can take psi of x and add it together with psi conjugate of x. All right? And why is this important? Because of the following, right? So whenever we have some complex quantity, we can always write it as, the real part of our quantity, in this case psi of x, plus I times the imaginary part of our quantity, in this case psi of x. So if we add psi, which is what we just wrote here, right, this is psi of x, with psi conjugate, which would be the real part of psi of x, minus I times the imaginary part of psi of x, right? Adding these two together gives us twice the real part of psi of x, which is real. And what if we take, actually let me change colors here. What if we take psi of x minus psi conjugate, right? In that case, we would have, let's see what we have up here. We would have the real plus I imaginary part minus the real, which would cancel out the real part, and minus minus. So we would get 2 times I times the imaginary part of psi of x. But since we're multiplying I times the imaginary part, we are going to get the real part because it's going to cancel out the already existing I. So we would get, well, up to a minus sign, right? We would get 2 times the real, or I don't want to write it as the real part of psi of x, but it would give us something that is real. Okay, so both this expression and this expression are always real. Okay, so that is very, very, very important. Now, we don't really know if psi conjugate of x is a solution to the Schrödinger equation, right? We don't know that. So all we did now is just show that we can write down a real solution if psi is complex, if we use psi conjugate. But is psi conjugate also a solution to the Schrödinger equation? Well, we don't know that. And even if it is the sum of two solutions also a solution? We don't know that either. So let's go through all of that. So the Schrödinger equation, of course, is minus h bar over 2m d squared psi of x. We already separated the time dependence here, as you can see, plus some potential that depends on x, and some psi of x, the wave function, is equal to e psi of x. So we know that that is the Schrödinger equation, of course, and for this equation, psi of x is a solution. We may not know what psi of x looks like, but we know that it is a solution. So what if we take the complex conjugate of the entire equation, right? That is perfectly valid. Then we have to take the complex conjugate of this, and of this. So let's do it. So the complex conjugate of the first part, well, the derivative doesn't change. All that changes is that now we have psi conjugate. Here we have the psi conjugate of the potential, so the conjugate of the potential, and psi of x, and the conjugate of the energy, and psi of x. But we know that the energy is indeed real, right? We just showed that in part A, so no worries there. And the potential also has to be real. I believe there's another problem I've done on this matter in my channel, but a complex potential, well, first of all, it's very, very odd, right? What sort of real situation is represented by a complex potential? There are cases, but we won't be dealing with any of those. So we can always assume that the potential is going to be real in this course, so no need to worry about it. So we can see that we get the exact same form of the Schrödinger equation, except that now the solution is psi conjugate. So we don't know what psi conjugate is, but clearly if psi of x is a solution, so is psi conjugate. So now that we know that psi of x and psi conjugate of x are solutions, right? And we know that psi plus psi conjugate and psi minus I psi conjugate are real. All that we need to know is whether or not the sum of two solutions to the Schrödinger equation is also a solution. So that is what we now want to see. So let's do this in general terms, because I don't want to have to do this derivation twice. So let's do it very general. So let's say that we have some solutions psi 1, which you can think perhaps psi 1 is psi, and we have some solution psi 2, which you can think it represents psi conjugate. And we have a linear combination of them, right? We have some psi 3, which is a linear combination, so C1 times psi 1 plus C2 times psi 2, okay? So you can think of this as the linear combination that we are seeing here, right? In this case, of course, in the first equation, C1 and C2 are 1, but in the second one, C1 is 1 and C2 would be minus I, right? But just some linear combination of any solution, okay? So let's insert this into the Schrödinger equation. So minus h bar squared over 2m, and we take the derivatives of psi 3 with respect to x, plus the potential psi 3. This is equal to energy psi 3. Okay, so now let's insert what psi 3 is, right? It is a linear combination of these three. Okay, so if psi 3 is also a solution, we should see that this does end up being true. So let's see. So we get minus h bar squared over 2m. Then we have second derivative x squared of c1 psi 1. I'm not going to write of x because I'm lazy. c2 psi 2 plus the potential times psi 2. Well, sorry, the potential times c1 psi 1 plus c2 psi 2. This is equal to the energy. So this is equal to the energy times c1 psi 1 plus c2 psi 2. Okay, so now let's just multiply through, separate everything. So we have minus h bar squared over 2m d squared psi 1 dx squared because of linearity, right? We can simply multiply through and separate them at the plus sign, and we can put the C1 in front here. So we have this, and we also have this potential that is multiplied by C1, so we can factor it out. So we get plus the potential psi1. Okay, and then we do the same for psi2, so we get plus C2 times minus h bar squared over 2m d squared dx squared, and then we have psi2, actually I wrote it a bit too far, there we go, psi2 plus v2 psi2, and this is equal to the same thing as before, okay? But what we have here is simply the energy times psi1, and this thing is simply the energy times psi2. So what we have is C1 times E C1 plus C2 times E psi2. And this is equal to what we had there. I don't think you can see it because of my camera, actually. No, but it is simply that. And it is E C1 psi1. So the C1 looks like a subscript. So C1 psi1 plus E psi2 psi2. And we can see that EC2 psi2 is the same as this. EC1 psi1 is the same as this. So yeah, this is indeed true. Okay, so now we have seen that any linear combination of two solutions will also give us a solution. So there we are. we are done, right? Because if any linear combination of solutions gives us another solution, and we know that there exists a linear combination of psi and its complex conjugate that always gives us our real quantity, then we can say, oh, if psi is conjugate, if psi is complex, we simply add it with its complex conjugate, or we subtract minus I its complex conjugate, we get something real. Okay, so we have seen now that any complex wave function can be written in terms of real wave functions. Okay, there we go. So that is part B. Now part C, which here it is, says if the potential is an even function, right? This is what we now want to prove, which means that minus the v of minus x is the same as v of x, then the wave function can always be taken to be either even or odd. So let's begin here by writing down the Schrödinger equation. So minus h bar squared over 2m d squared psi dx squared plus the potential of x. Actually, I'm going to write of x here. That's going to be important this time. And this is equal to e psi of x. So we know that for this case, psi is the solution. Again, we may not know what it looks like, but we know that it is a solution. But what if we take basically we go from x to minus x, right? What happens at minus x? So let's change x to minus x. Okay, so we have minus h bar squared over 2m d squared psi of minus x, right? We have moved a little bit. Then we have plus the potential of minus x times psi of minus x. This is equal to the energy times psi of minus x. So notice what we have. So if we have this Schrödinger equation for a given potential v of x, and we went from x to minus x, we have now a completely separate equation, right? We have now the Schrödinger equation for a potential that is v of minus x, and we have to solve this separately. But if v is even, that means that these two quantities are the same, right? So we can just write it like this, which means that these two equations are equivalent, and both psi of x and psi of minus x are valid solutions. All right, and what does that mean? That means that their linear combinations, like we saw in part B, are also a solution. So that means that we can construct some solution that is going to be the sum, right? I'm going to put a name here, but not yet. I want to show you why that name will be, what it is and where it comes from. So let's say this is, okay, psi of x plus psi of minus x, right? Both of them are solutions, so adding them together also gives us a solution. And I'm going to have another solution here that also has a pending name, and I will call it psi of x minus psi of minus x. Okay, so I know that both of them are also valid solutions. Now, what happens if in this equation I go from x to minus x, right? This is the parity transformation. Not really relevant, but I mean, it is important, but not for now. It will come much later in these courses. I just want to introduce you to the term. Okay, so this would be psi of unknown name minus x. I'm going to put a separating line there. This is equal to psi of minus x plus psi of minus x, which is x. So notice that we have the exact same thing as before. So that means that psi of unknown name of x is equal to psi of the unknown name minus x, which means that this thing is even, which is why the name that I will give it is simply psi plus. Okay, so this is even, so psi plus. Okay. Why psi plus? Because it is defined with a plus here, right? It's because of this plus. That's why this is called plus. Now let's do the same for this other unknown, even though I guess you may see where this is going now. So I will immediately call it psi minus. So if we go for minus x, right, we do the parity transformation, x to minus x, then we have psi of minus x minus psi of x. And what we have here is minus what we had before, right? If we factor a minus sign, right, psi minus of minus x, this is equal to minus psi of x minus psi of minus x. So that means that psi of minus x is equal to minus psi minus of x, which means that this is odd. Okay, so what is the conclusion here? The conclusion is that if we have a potential that is even, we can always write our solutions as a sum of even and odd solutions, and our result will still be completely valid. It will still be we can still work with it. And why do you, at this point, I'm sure you're wondering, well, why do I care about this? Well, because a lot of times doing this, right, saying, oh, we have even and odd solutions, and just working with them separately and doing this will be so much easier. Like, you cannot imagine. I have an entire problem about this. It comes later in this chapter where we apply this, and it is so ridiculously easier that you will be thankful that you know this. Okay, so pay attention, use this, even if you don't remember the derivation. It's not too complex, but it doesn't matter. Just know that if the potential is even, you can separate your solutions into even and odd, and soon enough, you will see a practical example of it, and you will be thankful that you know this. So there we go. I hope that you have enjoyed this video. If that is the case, please make sure to leave a like on the video, comment, and subscribe, and maybe even consider checking out my Patreon. So I'll see you in the next video. Thank you very much for watching.